This is the third and final part for the videos on chapter 36, absolute extrema in the extreme value theorem. So we're going to look at example 291. So what we have here is a man who's going to cross a river. River's 2 miles wide and get to a point 10 miles downstream. And he can row a rate of 9 miles per hour and walk 4 miles per hour. Remember that distance is rate times time, and so time is distance divided by rate. So what we want to do is we're going to write the time that it takes him to get from this point to this point in terms of a decision that we're going to make. Remember, with these problems, we're going to find a maximum and minimum. Here we want to minimize the time. And that time is going to be a result of a decision. And the decision is this: at what point along the shoreline will he pick to row to? So we're going to call this distance, so straight across the shore here, and we're going to call this distance x. So the part that he would walk is 10 minus x. Now what's different about this example as the others is the endpoints, the two extremes, are actually possibilities. If x is 0, that means you row straight across and then walk. If x is 10, that means you row the whole way. Those are two possibilities. Anything in between 0 and 10 is a possibility. So you literally have infinitely many points to pick along here. And you pick a point, you row to it, you walk. That's going to result in a time. And so we want to minimize the time based on that decision. Okay, so what is the time that it takes? Well, this decision results in this distance. We use the Pythagorean theorem. So this is the square root of x squared plus 4. That is the distance that he will row, and then 10 minus x is a distance that he will walk. So how long will it take to get from this point to this point? Well, we row square root of x squared plus 4. That's the distance that he rows. He can row at 9 miles per hour. Time is distance divided by rate. So we have 1/9 times the distance. This is the time that he will spend rowing. The time that he will spend walking is distance divided by rate. This is the distance he will walk. The rate that he can walk is 4. And so 1/4 times the distance is the time that he'll spend walking. This is the time he spends rowing. This is the time he spends walking. It might be that he doesn't walk at all, that he rows the whole way. It cannot be that he walks the whole way. He'll have to row at least 2 miles. So we take our function, we rewrite it in what I call a more derivative-friendly way. Write the radical as an exponent, distribute the 4 through here. So this is just rewriting the function. Then we calculate the derivative. Now we want to find the critical numbers, so we'll set the derivative equal to 0. So we rewrite the derivative in a way that makes that easier. We're going to solve this equation equal to 0. Refer to your notes. So in the interest of saving recording time and board space, I haven't put all the steps in here, but they are in your class notes. So look at your notes, you'll see the algebra. We get down to this quadratic equation that has no solution. 65x squared is greater than or equal to 0, set equal to negative 324. There's no solution to this quadratic equation. What that means is there are no critical points. So critical points, we have none. So remember, the extreme value theorem says a continuous function on a closed interval has a max and it has a min. Then the theorem after that says that max and min occur at either the critical points or the endpoints. There are no critical points, so the endpoints, one of these is our best solution. What does t of 0 represent? T of 0 represents rowing all the way across here. So our x is equal to 0. So t of 0 means we come this way and this way. This is our max. This is 49/18. This is greater than 2. T of 10 represents rowing the entire way. X is equal to 10. This part is 10 minus 10, which is 0. So we row the whole way. T of 10, 2, square root of 26 divided by 9. Square root of 26 is a little bit greater than 5 because 26 is a little bit greater than 25. So we have something a little bit greater than 10 divided by 9, which is greater than 1. The square root of 26 is less than 9 because 9 is the square root of 81. So this divided by 9 is less than 1, so this whole thing is less than 2. This is greater than 2, this is less than 2, this is our minimum. Okay. Now I want to make a disclaimer about this problem, and I want to warn you that it's not necessarily the case for the one that is in your assignment. You have an assignment that has a very similar problem, at least it looks similar at first. We didn't actually have to do any calculus to solve this. You think about it. Why? Shortest distance between 2 points is a straight line. So if we go from this point to this point rowing the whole way, that's our shortest distance. But remember, we weren't trying to minimize distance, we were trying to minimize time. But we can row faster than we can walk. So the rowing rate is faster than the walking rate. So here, going from here to here, rowing the whole way, represents the shortest distance with the fastest mode of transportation. So of course that was going to be the optimal solution. And we could know that really just from looking at the picture and these rates here. So we didn't even have to do any calculus to solve this. Not true for your assignment. For your assignment, I've introduced a current. And he's rowing upstream against the current. And because he's rowing against the current, rowing is slower than walking. Now, from here to here is still the shortest distance. But remember, you're not trying to minimize distance, you're trying to minimize time. So in the problem that you're doing for your assignment, walking is faster than rowing because he's rowing against the current. And so you'll have to keep that in mind as you're doing this problem. So my point is, that problem, the optimal solution might be between here and here. Again, because it's a similar situation, not rowing is not an option. You have to at least row straight across. That might be the optimal solution. It might still be the optimal solution is to row the whole way. Or it might actually be something in between because we're rowing slower than we're walking.